many times first order statistics and second order statistics, they are not enough to describe the random variables, and finding of higher order statistics becomes difficult when we go for higher order statistics. Moment generating function is a function by itself. It is telling you that it generates different moments for the random variable having different distributions. So computation of distribution, computation of moments when random variable is having different distribution. So how to find those moments of random variable? So that is what I am explaining through this video. So let us define what is moment generating function. The moment generating function is defined as phi x of t. This t is deterministic, x is a random variable. Phi x of t, it is a notation for moment generating function. X is a random variable, t is a deterministic variable. So phi x of t, it is a notation for moment generating function. Moment generating function, I told you that it is generating different moments of a random variable. It is after going through this video, you will understand that how moments can be easily computed by using moment generating function. So definition of moment generating function is expected value of e to the power tx, where t is deterministic, x is a random variable. This is the definition of moment generating function. And if you want to find this value of this, you can always find value of that by using this e to the power tx. T is deterministic constant, arbitrary constant, so e to the power tx fx x dx. So the random variable is taking different values. This is capital X. Okay, at every instant t we are getting different value. So this is the definition of phi x of t. Phi x of t is defined as expected value of e to the power tx. E to the power tx is an exponential function, no doubt. T is some constant or arbitrary constant, and x is a random variable. So naturally we are finding the mean. We are finding the mean of exponential function, right? So that can be written as like this. Since we know Fourier series as well as we know exponential series, in exponential series e to the power x, we can always write it is 1 plus x square by 2, then plus x cube by factorial 3, x raised to 4 by factorial 4, that is exponential series, right? So in this case also, since e to the power tx, let us say that tx is x. So by considering that, we can expand, okay, wherever x is there, put there tx. So t square x square factorial 3, t cube x cube factorial 3. So this is the expansion of e to the power tx using exponential series formula. So now use this operator. Expectation operator is a linear operator, right? It operates on individual terms. It is addition of terms, so it operates on the individual term. It is a linear operator. Since one is a constant value, expectation of constant is constant. T is deterministic, so t is pulled out. Expected value of tx is t into e to the power x. Then here t square by factorial 2, it is taken out, e to the power x square. T cube by factorial 3, e to the power x cube, and so on. It is infinite series, so we are having infinite terms. We know that we have defined non-central moments. Non-central moment zeta I is equal to expected value of x raised to I. It is ith order non-central moment. Using this fact, we can write this equation. By using this definition, the equation is modified, and we get equation in terms of non-central moments. So let us write this equation: phi x of t 1 plus here expected value of x and t. So mu x we can write zeta 1 t plus zeta 2 t square by 2. Likewise zeta n t raised to n divided by factorial n, and so on. So the said equation can be written in terms of non-central moments. So if you differentiate this equation, first derivative, second derivative, if you differentiate and take their derivative, we get d phi xt, first derivative I am writing, which is zeta 1 2 times t, derivative of 2t, derivative of t square is 2t divided by 2, so t into zeta 2 plus so on. Every term is having t, so rest of the all terms they are having t. So if I evaluate this d phi xt of dt at t is equal to 0, what we get, just see, we get zeta 1, since rest of the terms they are having t as a multiplier. So it is giving me the derivative of moment generating function, first derivative of moment generating function evaluated for t equal to 0. It gives first moment zeta 1, which is nothing but mu x. So if I go for second moment, d phi xt, d2 phi xt dt square, so what you get is double derivative of this equation, derivative of 1, so derivative of this is available, so derivative of that becomes 0. Now here we get zeta 2 at t equal to 0. Rest of the terms here, second if you go for second derivative, rest of the terms they will be having t. So zeta 2, it is expected value of x square, so it is giving me average of mean square value, average of square value, average of square value, or it is mean square value. So likewise, if you differentiate for nth order, if you take nth order derivative of this equation, you get nth moment dn phi x t divided by dtn. So this is nth order derivative, so definitely at t equal to 0 you get nth order moment, which is expected value of x raised to r. So to find the moments, this formula is very useful. What we have to do is we have to differentiate for and evaluate, differentiate and evaluate for t equal to 0. The first derivative gives first moment, second derivative gives second moment, and so on. Nth derivative is giving nth moment, so it is generating the moments of random variable x, right? So this way this moment generating function works. Now we will apply this to a random variable having binomial distribution. So random variable following binomial distribution, we will use this and we'll try to find the moments. So let us consider that a random variable is a discrete random variable and which has what we can say is binomial distribution. It is a binomial distributed random variable. So we know that probability that x is taking value k, that is n c k p raised to k q raised to n minus k. It is a binomial distribution. So where k is varying from 0 to n. So that distribution, by using the definition of binomial distribution, we can write the probability of that random variable x as p raised to k q raised to n minus k, and before that nck. So let us find phi x of t. Phi x of t, here x is taking value k. If x is taking value k, e to the power xt becomes e to the power kt, and k is varying from 0 to n. So n c k p k q raised to n minus k, it is coming from the binomial distribution. So here I am taking given function and that function is taking value k. It is the probability of that. E to the power kt, random variable x is taking value k. What is the probability that it is taking value k? It is p raised to k q raised to n minus k nck p raised to k q raised to n minus k. So we are, instead of vx, we are having e to the power xt, e to the power xt. So x is, random variable x is taking value k. The probability of taking value k according to binomial distribution is nck p raised to k q raised to n minus k. Now we can e raised to kt can be taken here, because here k is varying, and so there is no issue by shifting e raised to k. T is constant, so we can push there, and we can combine the term e raised to kt and p raised to k, and we can have a good expression out of that, and we can simplify and we can find pi x of t. If I expand that equation, after expanding this equation, that is pi x of t equal to k equal to 0 to n n c k p e t raised to k q raised to n minus k. It is just like a binomial expansion a plus b raised to n. So in the similar fashion, here if you expand this, you will get like that: nc0, nc1, nc2, nc3 a raised to 0 b raised to n, then nc1 a raised to 1 b raised to n minus 2, nc2 a square b raised to n minus 2, something like that. So it is completely that closed form equation. So that equation is a is what? P e to the power t, and what is b? B is nothing but it is q and raised to n. So you can write moment generating function of random variable x, moment generating function of random variable x when x has binomial distribution. Now do you want to find the mean of random variable x? Directly you can find mean. Pi x of t dt, take the derivative and put t equal to 0. So n times p e t plus q n minus 1, and derivative of this term is p derivative of this term e to the power t. So if I evaluate this pi x of t dt, and if I evaluate it for t equal to 0, what I get is n t equal to 0, in bracket we get p plus q, and t equal to 0 we get p plus q, we know that it is 1, so answer is np. And if you directly find the mean using your regular process, it takes time, so that time can be reduced by using moment generating function. In the similar fashion, we can go for second derivative, third derivative, nth order derivative, and by putting t equal to 0 in every equation, in every derivative equation, we get different moments. So in this way, the moment can be generated easily by using moment generating function. Thank you.